We start. Boop. All right. So as usual, I have the chat right here. Let me just change that around. Live coding 3. All right. So hopefully, if you have any questions, please let me know. I have it on the side right here. I hope everyone found the midterm not too hard. All right. Good morning, Alexandra, Jaren, Aaron, Adia, Tammy, and everyone else. Sorry. I decided to make this playground right here, just so that way we can do some experiments as we're live coding without having to jump around between multiple notebooks and unfortunately having things not work. So I hope this will work. And of course, you all have access to your own notebooks on Avenue, and you can make notes in your own notebooks, and then you can save them and refer to them. And as you can see here, with a little bit of HTML, you can make your own whatever coloring you'd like or whatever features you want. Are there any questions before we begin today's lecture? Any? I'm looking at the chat, so you're welcome to just type in the chat if you don't want to talk. Can somebody say some words, just so I know that you can hear me? Or that you're there?
Some words.
Some words have been said. Sigfa, yes. Hola. All right, great. Thank you. You know, when no one replies, I get concerned that I'm either too boring, which I probably am, or you know, maybe you're not there. All right. So today's plan is we're gonna move on to chapter 4. So if you're not comfortable with chapter 3, that ship has sailed. So please review the previous notebooks. Please reread chapter 3 if you need help with it. Ask on the course help channel. We'll try to help you out. But we're hoping that people are going to be comfortable with chapter 3, and now we're going to move on to chapter 4, which in particular will extend the left column of our proof style. Just refresh. This one right here. Okay, so usually it only has an equals or an equivales. Now we're going to have different operators, namely order operators. So that's the main reason we're talking about orders, so we can have them on the side. And our favorite order happens to be implication. And hopefully the next assignment will be out tomorrow. And surprise, surprise, it will be on order theory. So since implication is the main order you've seen so far, as well as less than or equal to, they won't be the ones covered in the assignment. We'll talk about different orders. And you saw some order theory on the midterm. So and I think there's some order exercises for week 5. Okay, so just order is a looser form of equality. So we'll talk a bit about that today. All right. Before we move on, actually, does anyone want to see what's wrong with this little calculation? All right. Can anyone guess what's wrong? Does anybody want to try? So let's try doing it together and see what we get. Okay. All right. So calculation 7 times 8 equals something. Somebody says 7 times 8 is greater than 42. 3 is less than or equal to 4. Those facts are not facts. Okay, yes. So 7 times 8, yes, is definitely greater than 42. 7 times 7 is 49. But what went wrong here? So let's try to find out. So here's 10 minus 3 times 12 minus 4. Does anybody doubt the first step?
We can't see your calc check window.
I'm sorry?
We can't see the calc check window if that's what you're in right now.
You cannot see my window. Well, that's unfortunate. I'm typing here. I showed it to you. I was talking about it. Well, that's unfortunate. So let's try that again. I want you to have access to the entirety of my screen. Okay. All right. Everyone can see my screen now?
Yeah, it works now.
All right, great. All right, thank you, random stranger. I appreciate it. As mentioned again, this is we're moving on to chapter 4 of LATAM. Okay, so here's the first step. That worked out fine. Just feel free to put it in the chat if you don't want to say it. What do you think the next step is the problem or not? Who thinks what? All right. 10 minus 4 times 12 minus 5. And this is equal by evaluation to something. All right. So everyone can see my code, just making sure. All right.
Yeah, we can see it.
All right, great. Great. This step is broken. All right. So does anybody suspect this last step? Evaluation, right? 10 minus 4 is 6. 12 minus 5 is 7. That seems reasonable. And then if we evaluate this last part, we get 42. So everything seems to be nice and dandy. So maybe these question marks are dubious. Maybe this one, fact 4 less than or equal to 5. All right. Does somebody think this is the dubious step? Maybe I shouldn't show. I won't show. I'll leave it. All right. Does somebody thinks something? All right. So the main thing we're going to be talking about today, so I'll leave it for a moment, is these tonicity theorems, right? Monotonicity, right? And in particular, monotonicity says if two things are less than or equal to each other, then when you replace them in an expression, you get a less than or equal to. So this is similar to Leibniz. Leibniz was talking about equal things. Leibniz says if you have equals for equals, you can substitute equals for equals. Monotonicity says if you have less than or equal to, then you can replace it to get another less than or equal to. This is the main difference. Leibniz is for monotonicity is for less than to less than. Okie dokes? That's the main difference. So but antitonicity, right, means you swap the order, right? So in particular, if you have a less than or equal to, the order changes, right? The D goes here and then on both sides of them, okay? So in particular, if you look at the second one, all right, C is less than or equal to B, we have minus B and then minus C, okay? So this is one moment. Shift? No. Shift tab. Okay, shift tab. This is the problem that went with the proof. This was the problem in the proof. Okay. When you have a less than or equal to and you're doing a subtraction, all right, it's not less than or equal to less than or equal to. It's less than or equal to greater than or equal to. It's swapped. Okay. So down here, we are swapping them. So 3 and 4, all right, this is in the wrong direction. It shouldn't be a less than or equal to. This is the problem. Okay. Yeah, so as someone mentioned in text, yes, this is the problem, right? 3 is less than or equal to 4, but subtracting them means it should be a greater than or equal to. Okay, so that was the problem there. So let's discard this and continue with the slides, and we'll come back to CalCheck Notebook as we need it or as you request it. So that's why I'm going to have that on the side. All right. So today we're just going to talk about sigma notation, as it's normally called. You've probably seen it in first-year calculus classes. And so the idea is, when you write this big sideways M, right? This is the Greek letter sigma, and it's supposed to be a capital S, right? And the idea is when you want to perform an operation a number of times, right? So we're adding an expression repeatedly. So to find out how many integral points are in this triangle, right? The number of integral points is going to be all the x and y such that their sum is at most n, right? That's what it means to be in the integral triangle. It's not a big concern if you know the meaning of this expression. The point of these 3 slides is just to show you the notation, okay? So we want to find the integral point, and we can express that as x plus y is less than or equal to n. And then we can simplify it and get it in this form. So this is the traditional form, using a capital sigma and writing stuff on top and writing stuff on bottom, writing stuff in front. So it's a 2-dimensional notation. You write a sigma, you write stuff on top, you write stuff on bottom, and you write stuff to the side. Okay, so you write stuff this way and you write stuff that way. So 2 dimensions. Okay. The problem with this 2-dimensional, the important stuff, like the variable, and so you might have seen in integral calculus when you write a fancy S symbol, or when you write limits. The problem is the main variable x is so squished down here, it's hard to see. The bounds are kind of squeezed in, and sometimes the bounds are really important, right? And not paying attention to them can make it hard to deal with these things. So we're going to use a linear style. Okay, so just as with ladies and tigers, we showed you some examples ahead of time just to tell you, hey, here's stuff you'll hopefully get to know in time. We're just showing you this calculation and saying, hopefully you'll get to know it in time. It's not a big concern if you don't know what's going on here. We'll get to these rules like nesting but 360, for example, you should definitely be comfortable with 360 and transitivity of less than or equal to. Okay, so we'll get to that in time. So let's actually talk about what these things mean. Somebody wants me to zoom in. That's not a problem. Okay, so that's not a problem. There you go. Okay, so we'll get to these in time. So let's talk more about this notation. All right. You're welcome. So what does it mean when we write this sigma notation? We write it in 3 parts. So you've seen a for loop maybe if you're in some programming. If you haven't, that's completely fine. But if you have, the idea in a for loop is you have some variables, okay, that you're going to talk about. Then there are some conditions on these variables, and then you're going to do something with them. So you might have seen set theory in first year, Math 1 CO3, for example, or other programming classes when you talk about a collection of things. So here we're talking about a collection of things, K, that satisfies this constraint, so they're less than 5. And we're really talking about K times K, where K is less than 5 and K is a natural number. So you kind of read these backwards. Okay. This is the sum of K squared, where K is less than 5 and K is a natural number. Okay. Or you can read it, the sum of all squares of natural numbers less than 5. All right. If somebody says, we'll zoom in on the share screen. Oh yes, okay. So somebody, all right, good, yes. So if you're looking at my screen, you can control scroll and it will zoom in on my screen using Microsoft Teams. All right. So let's try some of these examples out. I'm hoping. So if you don't want me to do something, please say so. Otherwise, I'll think you want me to do it and I'll spend time on it, which might be counterproductive. So does anybody? So I'm gonna show an example of this. All right. Okay, so here's an example. Let's change that up. Let's go back here. Okay, I hope I'll increase the size just in case it's not big enough. So it's the first one, right? So we're looking over all K. Let's use integers. Let's do 0, K less than or equal to 5. K times K. Okay, so the very first thing we can do is we can expand this. 5 is a lot. I'm just gonna do 3. I hope that's okay. 5 is a lot for me. So let's do k, c dot k. Actually, 3 is already a lot, but whatever. So the first thing we can do is we can split this up. So k is 0. That's the first thing, right? Command Z, because k is between 0 and it's less than 3. Then we have k being 1, and then finally we have k being 2. And we just write quantification expansion as the key hint, okay? And then everything else you've seen before. So we'll do some substitution. And that gives us 0 times 0, 1 times 1, and 2 times 2. Okay. And then we can evaluate. Evaluation. 0 times 0 is 0. Then you add 1. Then you add 4, and that's just 5. Okay. So that's that nice little sum. So let's talk about this. So let's remove all of this again, and let's talk about it. I want the sum. That's the first one. Did everyone see that? Let's go again. Slash SUM. I want the sum. What do I want to sum over? I want to sum over all k. What's the type of k? The type of k is natural number. What are some constraints on it? With, so let's do that again. WITH, with the constraint that k is non-negative and k is less than or equal to 3. All right, and then we'll put a spot. The spot is just to separate the constraints and the variable declaration from the body. Okay, and I want to do k times k. Okay, so let's write that down just a bit, just in case. So you say slash sum, then you have variable declaration, then you say slash width, then you have some constraints, then you say spot, then you have the body. Okay, so that's how it's done. Alrighty. Ooh, my spelling is off. Nobody check my spelling. Oh, I'll be sad. All right. Okay, so the big dot is just a separator. It's a syntactic separator. Okay. So let's look at this a bit more. Slash sum. Let's do I. Let's do i's of type not like this with 0 less than or equal to I less than n. Spot. Let's do some action. Let's suppose we have a function, right? So some function on I. Okay. Then this means f of 0 plus f of 1 plus all the way all the way up to f of n minus 1. Okay. All right. So where have you seen this kind of stuff before? Right. This is kind of a for loop, right? I'm going to do f of 0, then f of 1, and all the way to f of n minus 1. So you've seen this as a for loop or a while loop. Maybe if you haven't, that's totally okay. Or if you think, hey, this is an inductive definition, right? This weird looking thing with a bar and a spot. When n is 0, when n is 1, it's just f of 0. And when n is not 1, then you can split off a term and then you inductively define it. Right? So you can think of this sigma as another way to make inductive definitions. We'll get to these relationships between quantification and recursion, quantification and induction, quantification and loops later on. But I just wanted to mention that, right? So that this is a compact notation for essentially a loop, right? Or an inductive definition. That's essentially it. All right. So besides sigma, we can of course also have pi. Pi is a product. So instead of being a sum, Command C, we can do slash product. Oh, I spelled that wrong. Slash product. Okay, and product is just going to be a bunch of multiplications. All right. All right. That's all that's going to be. So for example, here we can say I want to perform the product of all of these guys, and everything's the same except this is now a product. It's a product, and unexcitedly, because we have a 0 in there, this whole thing becomes a 0. Okay. Ooh, something broke. Right here. Sorry about that. Change that into a. All right. Okie dokes. Ooh, I broke more stuff apparently. CalcCheck could not justify this step. I performed a substitution and then I added extra parentheses. 0, 0, 1, 1. Oh, right here. Sorry, I forgot about this one. Okay. Okay, so there, that's all there is. Yes, so it's colon equals, as usual, / colon equals for becomes. This is the substitution operation we talked about at the beginning of chapter 3 and chapter 2. So please review that. Okay, dokes. So last time we talked about the factorial definition, and we said the factorial definition, right, can be defined inductively. Factorial of 0 is just 1. So let's check that. Let's verify this together as a group. Here is a declaration. Factorial is a function from an n to n. Oh, axiom definition of factorial. I hope this works. Factorial of n equals, let's just put 0 just to make sure everything works. I'm not in a place where things won't work. Okay. So the factorial of this is going to be the product of all the numbers I of n with I less than n, less than or equal to n, and they have to be strictly greater than 0, and we just want to multiply all of them. Okay. So let's prove a theorem. Somebody asks, is there a theorem or axiom that you can use to go straight to 0 because it starts at 0? Yes, so there are a bunch of theorems and axioms for quantification. Today, I just really wanted to showcase it for you. So here's a theorem for you. Fact 0 equals 1. Let's try to show that. Factorial of 0 equals this big product, Command C, Command V, definition of factorial, place that by 0. Now look at this. This is a thing you proved on the midterm. This is called empty range, right here. This is empty range. I seem to have forgotten the keyword proof. In a rush to show you things, I need to slow down maybe. Malformed theorem statement. I forgot a colon. Factorial. My brain is thinking faster than I'm typing apparently. Okay, so if you recall this from the midterm, this is called empty range, right? And this is just false. Okay, and then if you evaluate the product of false, you get 1. So we'll get to the rules that let you go from here to here later on. So I can't. So this rule is called empty range, right? So we'll get to it later on. I don't even have it loaded right here, but in time we'll be able to prove these kind of facts. For now, I just wanted to show you these things. Okay, ducks. So here's another one, for example, the product of all odd natural numbers between 50. Here I want all numbers n less than 50 that do not divide, that are not divisible by 2. So this little skinny one, this is a fat operator, a fat bar. This is a skinny bar. The skinny bar denotes divisibility, and hopefully it will be the topic of the upcoming assignment over the weekend. Okay. So you'll be able to read these as the sum of all E where X satisfies R. That's one way you could read this. Another way you could read these expressions is the product of all expressions E where X is of type T. So you can, if we don't have a constraint R, we just don't write that down. We don't write the bar R down. Okay, this is an abbreviation. This is all chapter 8 right now, but you don't need to read chapter 8 if you're not interested. We're just talking about sums and products for today. All right. Okay, I'm just see if anyone has any questions, concerns, or queries. All right. So as I tried to mention over here on this side, the variable declaration, sorry about that. The variable declaration can have any number of variables. Okay, so it doesn't have to have just one. So let's try to see an example of that. Let's do a sum again, but instead of let's do 2 variables, and I want 0 less than or equal to j less than or equal to 2, and I want k to be as it was before, and now I'll multiply both pieces. Okay, so we'll have a jk with j comma k over here becomes some expression. Boop. So what does everyone think the first part is going to be here when we try to expand this? So we have 2 variables j and k. They're both integers, and we want j to be between 0 and let's just try 0 and 1. 0 and 1, and we want k to be between 0 and less than 3. So if we try to expand this, the first possible choice of j is 0, okay, and the possible choice of k is also 0. Okay, great. What else? What other choices can we make? Okay, so there's a formal way to do this called the split off term or range split, and we'll get to that later. But for today, we'll just use the keyword quantification expansion. Okay, so 0, 0, good. What else can I try? Well, j can also be 1, because 1 is greater than 0 and less than that. So I can make it, well, and I can also make it 1. Okay, great. And I can leave k alone. What else can I do? All right. Another thing I could do is I can say, let me take j to be 0 again, and this time I can take k to be 1. Okay. Okay. And I can take k to be 1. Great. What's another thing I can do? Well, I can take j to be 0 again, and I can take k to be 2. All right. All right. So 0, and this one is 2. 2. Sorry. Yes. So I can have j to be 0 and k is 2, or j is 1 and k is 2. Okay. All right. Everyone is putting in. Yeah. So this is exactly. Yes. So the idea of using quantification is actually to help us prove loops are correct. That somebody got it right on the money. Good job, Shrill. And the idea of having multiple variables, which a lot of languages let you do, like Python and other languages, will let you do a for each over multiple variables. It can be thought of as a nested loops or nested quantification. Just as you can have simultaneous substitution, and simultaneous substitution can be written sometimes awkwardly as sequential substitution. Likewise, multiple variables quantified can sometimes be written as nested quantifications, and we'll get to that. There's a rule for that called nesting. Okay. So I have a plus sign everywhere. So I have this guy plus that one, plus this one, plus this one, plus this one, plus that one. I specifically separated the plus signs to show you, hey, here j is 0, 1, j is 0, 1, j is 0, 1, and every time we pick a different value for k. K is 0, k is 1, k is 2, right? So it's like a for loop. For each j being 0, so a k stays 0 both times, k stays 1 both times, and k stays 2 both times. Okay, so I separated it visually, that was all. So we can perform some substitution, and let's do evaluation at the same step. So the first one is going to be 0 times 0, that's just 0, plus 1 times 0, so that's also 0. Then we're going to have 0 times 1, which is 0. Then we're going to have a 1. Then we're going to have 0 times 2, which is 0. Then we're going to have 1 times 2, which is 2. Okay? You're welcome. So notice I'm putting 2 words in here, right? I'm putting 2 hints inside the step, and you'll be able to do that hopefully for the next assignment. And we've only been letting you do 1 step at a time to avoid confusion. So going forward, you will have multiple hints allowed. We'll usually let you know how many. Okay. And let's do one more evaluation, all right, to get us to 3. Okay. So you can have multiple hints. You can separate them by the word and or by a comma, as CalcCheck treats it. But I just wanted to show you this feature. You'll hopefully see it on the upcoming homework. All right. So for now, we're doing just sums and products. But we'll, of course, this is just a generic notation, right? So we just did some of these examples, and here's some contrast between the classical. But of course, as some of you probably realize, we can go all the way and replace this by /O plus, and right here, /O plus, right here, /O plus, and right here, /O plus. Okay, so we can do this generic form as well. All right, so I hope you see that it's not unreasonable to go all the way to the generic form. All right. Okay, so the quantification right here essentially just denotes a loop, right, or an inductive definition. All right. If you're not comfortable with this idea, don't worry. We'll work on it and we'll try to hammer it home over the little while. Alrighty. Okay, ducks. Okay. So hopefully with that part done, let's go back and actually focus on chapter 4 of LADAM. The main reason we talked about quantification is hopefully that we can do more program correctness things with loops. So that's the direction we're aiming towards. But along the way, we want to, you might have noticed at the end of chapter 3, our calculations got really long, especially when they involved implication. And so chapter 4 is a way to make our calculations shorter again. Okay, so let's talk about that right now. What does it mean to add a new operator on the side, right? What does it mean to add a less than or equal to? Because before we talked about what it meant to have an equality, right? We said when you have an equality, right, you start off here, you slide all the way down because they're all equals, and you end up here. Okay, so you start at the top and you have a bunch of equals, and because equality is transitive, you just absorb those equals, you chain them up, and you get an equals at the end. Okay. So this is the transitivity rule in case you have forgotten, right? If I have all of these guys, then I get the last guy down there. All right. So, and this of course relies on the fact that everything is treated conjunctional, right? When you have things on the side, you treat them as the first two and the next two and the next two afterwards. So you treat it conjunctionally. And then by transitivity, the first one is equal to the last one. All right. So what if we want to put a less than or equal to there? Well, less than or equal to is also transitive. So when we have equalities on the side, right? Let me freeze frame. When we have equalities on the side, right? And we start with one thing, and we start with one thing right here, we can slide down and make it all the way to the other side. And this is, of course, because at most is, again, transitive. Okay, ducks. Just trying to make sure no one's texting. All right, you're all good? Okay. So the main hindrance we've seen is an implication change, and we'll show you how to get around that in a moment. Right. So we're just talking about general orders. It doesn't have to be less than or equal to for numbers. It could also be implication. The same reasoning will work. So let's move on there in a moment. Okay. So when we use an implication, right, the same thing will happen. If you recall, we had some of the theorems like this for transitivity, all right? Let's remove those. You start off here, you slide down there, and you go here, okay? Because you can replace equals for equals, right? So E0 implies E1, but I know E1 is the same as E2, so I can replace E1 with E2. But I know E2 implies E3, so I can glue all of that together, or transitivity along with Leibniz, to get E0 implies E3, okay? So when you have a mixture of an order and an equality on the left-hand column, now you need not just transitivity, but you need Leibniz as well, which we already have, okay? So that's what we can do to put orders on the left-hand side of the column, all right? Okay. What about when you have different kinds of orders, all right? So here we have a less than or equal to, then an equals, then a less than. Luckily, we can prove, right, that when you have a less than and a less than or equal to, the less than absorbs the less than or equal to. So we have a less than and a less than or equal to. The result is going to be a less than. Okay. So when you make a calculation like this, right? You start off with E0, you slide all the way down, you get to E3. Now you ask, what's the result? Well, at this stage, I have a less than or equal to. And now I have an equals, but equals and less than or equal to, which one is more constrained? Equality is weaker, so at the orange box, we have a less than or equal to still. We have a less than or equal to right here. Let me just write that down. Here we still have a less than or equal to. All right. Then by the time we decide to move all the way down here, okay, let's put that right there. Okay, we have a less than or equal to and a less than. Which one is weaker? Well, less than is definitely stronger, and so at this step we have a less than, and so the result of the whole thing is going to be a less than. Why does the second hint have a with comment? Because it's an equality. I'm just explaining why these things are equal, and I'm just reminding you, hey, you can put comments in there, right? Explaining why these two guys are equal, right? Or other justifications, all right? So you've always been able to do that. Just wanted to mention it. So the relevant theorem becomes if you have a less than or equal to, right, and the less than is stronger, right? And so the whole thing is going to be a less than, okay? And as usual, you use Leibniz or replacement or the replacement theorems 384 to make use of any equalities along the way, all right? But notice they're all in the same direction, right? The less than points, less than or equal to points this way, this one points this way, they all are in the same direction. And you have a related theorem that justifies why this calculation shows E0 is less than E3. If you mix the directions, we have an at most pointing to the left and an at most pointing to the right. Now it's not clear. Conjunctionally, this reads this way. And what do we conclude from this? E0 is at most E1 and E2 is at most E3. Do I slide down? Do I slide up? It's so when you have opposing operations, things can get complicated. In particular, they can get nonsensical. All right. So we'll work with this as we see more operators being put on the left-hand side. This particular idea of putting hints in the middle will come up again in the form of a with combinator, and it will help us. It will help make proofs even shorter and shorter. Okay. So we talked about this. Let's show an example. So this one was from earlier, but I'd like to show you one involving implication. So let's try that. Calculation. suppose I have two things, P and Q, okay? Then I definitely have P. Does anybody know what this theorem is called? Does anybody know what it's called? Just curious. It's called weakening, right? So this is called weakening, right? So I have P, so I can do another one. There's another theorem also called weakening. If I have P, I definitely have P or Q. Okay? All right. So I've just shown P and Q implies P or Q, which makes sense, right? If you think of it as x minimum y is less than or equal to x maximum y. Okay, so if you think of it this way, then this calculation sounds reasonable. Ands are weaker than ors. Right? So here's a cute little theorem. Now let's try proving this theorem without having stuff on the side right here. How would we do that? It would be very difficult. So P slash and Q, we want to show that this is equal to P or Q. Where do we even start? All right. Does anybody even know where we start? All right, so this looks very tricky. Where? All right, this is, oh my gosh, so hard. Okay, like, so as an exercise, try proving this, right? It looks really easy, and using the extended proof style, it's really easy to prove. It's 2 steps, but try doing it, try getting to true. Yeah, all right, fine. If you use the definition of implication, it's really hard. But someone here is very clever, Shrill. Shrill says it's not that hard. All right, fine, Shrill. You know stuff. So we can do shunting to get P implies Q implies P lower Q. And then we can say this is just weakening to get P implies true. And then we can say write 0 of that guy to get true. It's 1 step more. It's a bit hard. All right, it's still 1 step more. It's harder. You have to know about shunting, and maybe you don't know about it. All right. So this was easier. The idea is weakening. Here we had some bookkeeping. We had to do shunting. We had to do a write 0. We had to do some bookkeeping. Also, this one is more exploratory. I started here, and I just showed you this part of the calculation. And then for fun, I decided to show you more. So this style is more exploratory. You can go on an adventure and try things out. Whereas this style, I have to know the whole thing. And now I'm just verifying that it's true, right? Here, we're going on an adventure, trying things out. That's what we're doing, trying stuff out. Here, somebody told us it's true, and we're just checking, boringly checking that it's true, okay? So hopefully, you'll see bigger examples, and then I'll become clearer, hopefully, why this helps with longer proofs. So whenever you have an implication right here, you can try to make it into a proof like this. So try looking at all the theorems you've seen before that have an implication and see if you can try to prove them this way. All right, some fun stuff. So I want to go back to monotonicity, just in case it's not clear, and in case you're interested. You just HTML tags. That's it. Right. So here's a summary. Right. Hello. Right. Control Alt Enter. Control Alt Enter. Right. And then it just becomes a toggle. So, right, toggle to see what's going on. So you've seen this a lot on the abridged lecture notes on the web page I keep. I do a lot of these toggle things, and you can do them yourself in your own notes. All right. Control Enter. So these monotonicity theorems, I just want to mention again, Leibniz is about equality, substituting equals for equals. Monotonicity is about substituting inclusions for inclusions. Okay, so let's, again, monotonicity, inclusions for inclusions, whereas Leibniz is quality for quality. So these are the main mantras to remember. Inclusions for inclusions, even though I spelt that wrong, and Leibniz equality for equality. All right. Okay. So we can talk about the HTML you can do, and you can try it out. We can talk about changing the background color. I can, but let's just wrap up a little bit more about this. So this is what I mentioned at the beginning when we showed that calculation. I should have kept it around. So isotonicity means monotonicity in one way and the other way. Okay. So this is what we'll do with the keyword with. Okay. So with is for discharging premises. So notice all of these guys they all have an implication in them. So how do you actually use this? Well, to use these guys, you first get rid of the implication. All right, you get rid of that, and that gives you a new theorem. All right. So if you recall, before we had the substitution inference rule, which gave us new theorems, and we said we can use Leibniz to get new theorems. And so now we're introducing this with keyword, and that will give us a new theorem. Alrighty. So you'll try it out a bit more, so don't worry too much. We're just showing you the basics of monotonicity and quantification. We just want to show you these things. So it's not a big concern if you're not comfortable with it just yet. All right. But maybe let me say a few words about it, just to try to make to remove any doubts. So suppose you have a theorem premise, right? Some premise on variable x. Then you can have some conclusion on that variable x. Okay. And suppose I have some given claim G that says I have the premise for x0. Okay. All right. For a particular x0. And let me try to make this clearer, because some of you thought this was confusing. This is true. Okay. All right. How with works. Okay. Then using these two together, all right, I have this new theorem, T prime, which is conclusion with 0. All right. All right. This is T with G. Okay. Okay. So this is how the phrase with essentially works. Okay. Oh, forgot about new lines. Okay. So if you have a theorem T and it says if I know some stuff about X, like the monotonicity theorems, right? Then you can have some conclusion, and you already know the premise for x0 is true. Then when you say T with G prime, T with G, you get the result of that conclusion. Okay. So another way, and you might have seen this before, P implies Q, and I have P, right? So that's called modus ponens, right? Calculation P, and I have P implies Q. Does anyone remember what this is? I just said it a moment ago. Okay. All right. So this is just modus ponens. All right. Could not justify the step P and, oh, sorry, this is an implication, right? If you have P and you have P implies Q, then you have Q, okay? So to use modus ponens in the middle of a calculation, we're using the phrase with. Right? So under the hood, with is doing a modus ponens, okay? So let's just write that down, modus ponens in action. Okay. All right. So it seems my time is up. I just wanted to show you this last slide about how antitonicity removes things. So in the first argument, it's OK. In the second argument, it's antitonicity. And anyhow, thank you for attending. I hope you like this idea of using a playground. feel free to ask questions, and I'll continue doing stuff like this in the future, just so that way we can show things in CalCheck alongside slides. I hope you have a terrific Thursday, and yeah, bye. As usual, I'll be here to answer questions